Okay, looks like we're recording. So here's where we were last time. We were talking about parameterizations, and we looked at this one. Here's a function from R1 to R2. Because the domain is R1, seems like the image, namely that which we are parameterizing with this function, should be a curve. Right? One-dimensional domain, we should have a one-dimensional image generically. Okay. And then this being the function, question comes up: what is this? What is this curve? And despite our sort of expectations that it would be curvy because there's cubes in there, what we find is that in fact the image, every point that comes out, this x and this y, satisfy that pretty easily identified relationship, and so in fact all these points are on that line. In fact, it parameterizes the entire line. So a little bit unexpected. One of the big morals here, again, is one of the last notes that we talked about last time, is what this means is that if you have a curve, there are lots of different ways to parameterize it. This is a good news, bad news thing. That's kind of good, I suppose. Gives you more flexibility in how to parameterize, how to do what you want to do. On the other hand, this means that looking at images is a flawed way of understanding functions. Then again, aren't they all? Right? So that's one of the flaws of looking at images.
Wait, so do you just notice, like, oh, it satisfies this line, or is there a way to solve that?
Well, so what there is not is a single algorithmic process that will always yield the answer, right? So sadly, that's not a thing. What there is there are different ways that you can, hopefully sometimes, there are different tools that in some circumstances work. In this circumstance, you sort of notice that the x and y seem to have something in common.
Would that just be by writing out a bunch of points?
I'm sorry?
Would that just be by writing out a bunch of points?
No,
I don't notice it. I don't see how.
Okay.
We notice every output point satisfies this equation. I just don't see that.
Oh, yeah. So the way we notice it is by when you look at that formula for, keep in mind, this is x, right? Mm-hmm. And you look at this formula right here, that is y. What I'm saying is we should look at these formulas and ask yourself, are there similarities in these formulas? Any sort of relationships between these formulas that might make it possible to find an algebraic relationship between them. So you have to, I'm not saying that you'll notice it despite effort, right? I'm saying you should expend the effort to, make a point of looking at that and asking, are these in any way things that if I were to manipulate one of them, I could make it look like the other?
Oh. Okay.
That's what I'm saying. Yeah. Okay, yeah. Right, and you look at these formulas and well, they kind of look. They have a certain amount in common because they both have cubes in them, and then it's kind of all over but the details. Yeah, right. And we will have other tools as well. I'm going to show you some other different things that work in different circumstances. Yeah. Okay, so you may have noticed that in both of the examples that we've done so far, last time that was, the input variable that I chose was t. This was not an accident. I did this on purpose. Excuse me. That's a common choice and a common way to interpret, to think of the input variable as being time. It's just a point of view. You don't have to do this, but it's really convenient, really handy. And by the way, an important part of lots of the applications that we're going to do. So there's that. But thinking of the input as time, notice that what these parameterizations turn into then is it's not, output position as a function of, some arbitrary input variable. It's output position as a function of time. We are describing location as a function of time. If you think about it, location as a function of time means you're describing a process of moving through the target. Right? Position as a function of time means you're moving. So here is an example with that in mind. I like this example of a snail crawling around on a plane, right? For two reasons. One, it's kind of funny. And here he is. There's a little snail crawling around, and he has a position that depends on time, right? When t equals 0, maybe he was here. When t equals 1, maybe he was here. T equals 2, taking a hard right turn there, etc. The other reason I like this idea of it being a snail that's moving along is, I don't know if y'all grew up with snails when you were kids or whatever, but at least the kind of snails that were around my house when I was a kid, they leave this trail of slime. Right? So, it is that trail that is the curve that is the image. Right? So we've got a function that's describing the snail's position as a function of time. The image of that function is still, what are the output values? What are all the different locations the snail has been? So the trail of slime is the image. Now we want to distinguish between that curve, which is just an inert thing that just sits there, versus the snail's process of moving along that curve, right? One of them is an inert geometric object, a static thing that just sits there. The other is a process, right? The process of the snail moving along is a different thing. Different metaphor, you might distinguish between the road versus the road trip, right? Which I think sounds kind of poetic in a way. But the road just sits there. It was there yesterday, it'll be there tomorrow, right? It's just not moving, it's just sitting there. The road trip is the process by which we drive along it. Some people might have one road trip where they drive really fast. Some people might have a different road trip by which they drive really slow. What you've got there is different parameterizations, different road trips, across the same road, namely on that same image. Right? So again, different, one curve can have different parameterizations. One road can permit different road trips. Okay. All right. Okay, here's one way that you might sort of represent some of this. Here is a line. This is that same line. Oh man, this is that same line that we looked at last time. Same line, same road, but two different road trips, two different parameterizations. We saw those two different parameterizations last time. In the first parameterization, it was what you might call linear, in that you were moving at across that straight line at a constant speed. Right? The other one was cubic, which means that we were moving really fast over here, and then slower, and then for at least an instant we were actually stopped, and then started to move again, and then started moving really fast later. So, again, very different road trips across the exact same road. And you can kind of represent that geometrically by putting down a couple of checkpoints of where were you when, right? We were here that first night, and second night we stopped here, third night we stopped here, etc. Well, this was a very different process. Really fast driving for a while, slow driving, a lot of sightseeing maybe over here, fast driving later. Okay. Does anybody have any questions about what we're talking about? Does everybody see the difference between the curve, namely the image, versus the parameterization of that curve? Everybody happy? See the difference between the road and the road trip? Okay. All right. Okay. More examples. Y'all can read this example. It's, whatever. Here's a nice one. This is a classic example. Let's look at, this is a parametric curve in R2. Here's the formula for it. Note X and Y are functions of time. And, okay, so the game begins. Can we find an algebraic relationship between this X cosine t and this Y sine t? And, you can play with it in various different ways. You could ask, what can I do to cosine t to make it look like sine t? There's the whole Pythagorean relationship. Square root of 1 minus cosine squared gives me sine. Well, okay, technically it gives me the absolute value of sine. But anyway, that's sort of suggestive an algebraic relationship. And likewise the other way, but the cleanest way to find this relationship is to notice that the Pythagorean relationship itself, you don't have to solve for something in terms of something else. That directly tells you that x squared plus y squared is 1. So we know that, of course, that is a circle. That's this unit circle here. So we know that this parameterization here, that is a parameterization that's part of this circle. So it's only moves on the circle. Now, where does it move on the circle? Does it go around, or does it just kind of go back and forth across the right edge over here? That, we don't know yet. Right? But there, with a little plugging in, you can persuade yourself. Well, let's just see what happens when you plug in a value of t. Let's start with t equals 0. T equals 0 puts you here, easily determined, right? And then you can just ask, well, what happens as t increases? Well, as t increases from 0, sine t increases all the way to 1, which means it's got to do that. That's the only way that y coordinate can make it all the way up to 1 from that point, going upward. And then, et cetera, continue to, think about what happens to the various different coordinates. What happens, I guess we can stay on that y coordinate. What happens next as t continues to increase? Well, sine t goes down to 0. And cosine t, starting at t equals pi over 2, cosine t decreases to -1. And that means that you've got to do this. So you can just think about the behavior of the sine and cosine function and persuade yourself that, in fact, this just continues to go around and around that circle. Everybody happy? Okay. Classic example. Good example to make sure to remember that if you ever need to parameterize the unit circle, that's a great way to do it. Very handy. Definitely one to remember for the future. All right, here is a variation of that. Now, this is a harder one. This is going to be a new tool for your toolbox. Function from R1 to R3. Okay, so this is a parameterization. We know this is a parametric curve because we can see that the image is one-dimensional. The target is R3, so this is a curve moving through space. And here's our formula for it. X, Y, and Z are given by these formulas. And wow, so, man, can I think of some algebraic relationship that involves all of these coordinates? X, Y, and Z. Ooh, that's going to be tough and tricky. I mean, you can see some relationships. You can see the whole cosine sine thing, right? So X and Y, we have a relationship. Well, what does that have to do with Z? What's Z doing? Is there an algebraic formula that's going to relate Z to X and Y? And that's hard to see. I'm going to, loosely speaking, say that's not something we can realistically do. So here's the new approach I'm going to show you. This is, again, just a different tool for your toolbox. This is not an algorithmic process by which you can always get answers by following certain rules. The new point of view I want to give you is just think about different aspects of this curve separately and then bring them together. So step 1, as we've already recognized, X and Y are moving around in a circle. So that tells me, I'm just going to hand wave here, that tells us that the X and Y coordinates are doing this. Right? I don't know what's happening Z-wise. Right? But the X and Y coordinates are doing like this. So you might say, if you like, that this curve is confined to this cylinder. The cylinder with the equation x squared plus y squared. But more than that, as time passes, the X and Y coordinates are kind of moving around the cylinder. Yeah? And here's another observation, and this is an independent observation. Independently, I notice that this formula for Z is really easily understood. Z is T. As T increases, Z, which is also t, just increases as t. I mean, so here's two things that I know about this curve. I know that the shadow down in the xy plane is doing exactly this. And here's a coordination test for me. The z coordinate is doing that. So I know I've got two different kind of. I've got pictures of this point moving from two different cameras. Right, I can see directly from above, if you will. I can see that it's going around in a circle like this. But I also know that as far as the z coordinate goes, it's going up at a constant rate. And if you think about it, you just combine these two observations, and it tells you exactly what this curve is doing. This curve is doing this. Right, it is in the xy coordinates. It's going around in a circle. The z coordinate is rising. It is tracing out a helix, a slinky. Everybody on board? So this is different. We had to, invoke some geometric intuition to come to this conclusion. This is non-algorithmic, but it's a different way of breaking it down that gives you an answer. Yeah. Mm-hmm.
What's this process called?
Not aware of it having a name. This is just a point of view that you can use to figure this out. That's all. Yeah. Anybody else? Okay. All right. So here's another way of figuring out what you're looking at. Let's look at this parameterization. Now you can see that we have x and y as functions of t, so this is a curve moving through the plane. And I guess you could, if you got real clever with it, you could make some algebraic relationship between x and y there, but it's going to be a weird and tricky one, and it's not the preferred way to do this. I think you'd find that it's less desirable than ideal. But anyway, here's a different way, certainly, that you can approach this, and I think very nice, and that is to rewrite this vector-valued function, interpret it as a vector. Don't think of this as, well, there's the first coordinate, and there's the second coordinate. Think of this as a vector. And breaking it down as a vector, you see this. So we've separated out that there is, on the one hand, this one vector, t comma t. That's easy to understand. I know what that t comma t is doing. And then there's this other vector. Well, there's negative 1 comma 1. That's easy to understand. That's just constant, right? But, okay, we don't technically have exactly negative 1 comma 1. We have sine t. We have a scalar value function multiplying by that simple negative 1 comma 1. Okay. So let's draw pictures of these things. And not hard to persuade yourself, t comma t is going to be a point like that. That's just moving along that straight line. That's easy. Negative 1, 1. Well, that's too long, isn't it? Here, I'll go into pencil mode. Actually, let me do this in pencil mode, too. So, there's t comma t, moving along that straight line. Negative 1, 1 is that vector. And as time passes, I'm not going to be looking exactly at negative 1 comma 1. I'm going to be looking at sine t times negative 1, 1. So what does sine t do? Well, it starts off small. I'm going to start off with a small multiple of that vector. Then sine t increases. I will get up to a full 1 times that negative 1, 1. And then as time continues to pass, this scalar gets smaller. So roughly speaking, that purple vector is going to kind of do like this. So it's going to be like that, and then that, and then that, and then back down to that, and then a smaller, and then it's going to go over on this side. It's going to be bouncing around like that. So what happens when you add these things? Well, the way we add vectors, of course, is head to tail. What I've drawn here is the green vector separately, the purple vector separately, but now let's add them. So as time passes, let's put these together. We're going to start off with, a point there, small value of t. The purple vector for a small value of t is going to be something like that. A little bit more time passes. Green vector's moved along. Purple vector increasing. Right? And as time continues to pass, purple vector starts to come back down a little bit. Green vector keeps moving along straight away. Keeps going. Time passes to where sine t is negative, etc., etc. And the sum then, when you add these two vectors to each other, as I've got them written here, you can see we're doing head to tail for each of these values of t. And you can see it's a curve like that. It's it's basically it's a tilted sine wave. Everybody on board? So what's the moral of that? I don't know if this necessarily has a proper name, but I would say you can do a vector breakdown of a parametric curve, and that can be really useful. And I'm going to show you an example where we can make good practical application of this point of view. Okay, alrighty. Okay, so let's talk about parametric surfaces. They're a lot like parametric curves. The big difference is that instead of having one input variable, we now have two input variables, u and v. I appeal to your memory of the argument we made last time. With one input variable, as that one input variable moves in only one direction, you sort of expect the output to move kind of correspondingly in sort of just, in different directions, but it would just be it would trace out a curve corresponding to the one dimension of that input variable. With two input variables, the picture is analogous but a little different, right? With two input variables, then, that point might go there, you might say, right? Then as you go in that direction, maybe it traces out a curve. Then from there, as you go in that direction, maybe that traces out a curve. But then, hey, from here, as you go in that direction, that's going to trace out a curve. And then, from there in that direction, that's going to trace out some sort of a curve. Wherever you are, you might say, there are two different directions from which you can go in the domain. And then analogously, then on the image, wherever you are, there's kind of two different directions that you can go. So my appeal is that because then this is two-dimensional, it is the fact of this being two-dimensional that makes us kind of expect, generically, exceptions granted, there are some weird anomalous oddball things that can happen, but generically you would expect to have a two-dimensional image. How's that seem? Is that kind of plausible seeming? So again, we call this the image of the function. And again, analogously, we call the function a parameterization of the surface. So you can think of this as a way of, this picture here, this image is a way of getting some understanding, some geometric understanding of this function. Thinking of the picture, thinking of the image is kind of a sort of a competitor to the graph construction. Graph is a picture that helps you understand a function. Level sets are a picture that help you understand a function. Very different picture. Well, images, likewise. This is a different kind of picture. It's not a graph. It's not a level set. This is a third, qualitatively, fundamentally different kind of picture that helps us understand this function. But then it also goes the other way. This is also a function that's going to allow us to get a better understanding of the picture, and that's going to be, again, a big deal, just like I claim it's going to be a big deal for parametric curves. Okay. So an example. Oh, here it was. I just passed it. Here's an example. Look at that function. Don't forget, when you have a parameterization, these outputs are variables. That's x. That's y. And that is z. Right? So, just like we did with parametric curves, it'd be pretty reasonable to think, well, can I find some algebraic relationship between these things? And good news, if you think about it, because we're now looking at a surface in space. A surface in space is typically described by one equation, right? So instead of having to, when we had a curve in space, we need to kind of understand two different points of view to understand what that curve is doing. In some ways, there's a lot more ways that a curve can bend around in strange ways, that it's got more degrees of freedom in some sense. Here, this being a surface, we expect there to be a single equation that describes that surface. And for example, again, just with a certain amount of kind of playing around with it, you can find, suspecting based on the fact that these formulas do look a lot alike, a little bit of playing around, you can persuade yourself that z is 2x plus y. Now, that you got to play with it, right? It's not, you're not just going to consult your inner oracle, and then just write it down, right? So, mess around, try to think strategically about, what can you do to turn these things into those things, and what have you got to do to make that happen, and eventually you can come up with a result like this. Okay, so what we conclude from this is that this parameterization sits inside of this plane, and in fact it turns out, and let's not worry about this little detail, but it further turns out that this parameterizes the entire plane. Okay. Alrighty. Yeah.
So back to the picture for the image,
this one here?
Yeah.
Uh-huh.
So how would you draw it like that?
This is just intended to be a generic picture. So the idea was that, you remember we drew something similar with curves. We say, well, this point here has got to go somewhere. And then we say, well, this point here is nearby, so we figure its image is going to be nearby. And I just kind of, one curve at a time, or one point at a time, tried to persuade that, well, as you move in the u direction, you kind of generically expect to have a curve. Right? And so I'm trying to make an analogous persuasion here, and this is not a rigorous argument. It's not intended to be rigorous. Just an analogous persuasion that generically you would sort of expect, because from any point you have two different directions that you can go in the domain, right? That in the image, as you move along, you kind of generically expect to have some sort of a shape on which you have two directions that you can go from that point. And that just kind of suggests that it should be a surface. It's just a plausibility argument, that's all. Does that help? Is that good? Okay. Yeah.
So basically just then the number of input variables in the domain defines the context of the surface.
It suggests. I prefer not to say it defines, because there are counterexamples, there are sort of anomalous, annoying sort of things that can happen, but mostly generically, typically, what you said, the number of input variables, namely the dimension of the domain, suggests the dimension of the image. Yeah. Is that cool? Anybody else? Okay. All right. Okay, let's see another one. This one here is a little scary at a glance. Right? There's a lot of trig all over the place there. But what you'll notice, and by the way, especially in the context of an exam or a homework question, you have one additional tool to work with, one additional piece of information with which you can strategize, which is that, well, yeah, but this is a question. That means there must be some reasonable way for me to get my hands on this, because otherwise it would be, Bray's not going to give me an intractable question, right? That wouldn't be fair. So there's got to be some sort of a foot in the door here. Now, what could we possibly, thinking sort of outside of, the box, does this remind me of anything, for example? And you may just make the observation that, it vaguely kind of reminds me of all those sines and cosines we saw in spherical coordinates. And then you notice, oh my God, this is exactly the arrangement of the sines and cosines in spherical coordinates. There's no rho in there, right? But said differently, with rho equal to 1, this is exactly the formula for spherical coordinates. Okay? And so what that tells you then is that this point in the domain here is just telling you the phi and the theta for a point in spherical coordinates with rho equal to 1. So this is parametrizing the unit sphere. Yeah. So now, I'm not suggesting that you will always get this lucky, right? But I am suggesting that I'm not gonna do something unscrupulous on the exam and give you something where there is no foot in the door, no way to do it. And sometimes the foot in the door is that what I give you is in fact familiar. So be on the lookout for that kind of thing. By the way, this is not a manufactured type of situation. Life is full of fortunate coincidences. The world is full of symmetries, right? The world's full of circles. The world's full of spheres. So it is not at all surprising that at some point you might find yourself looking at this and then realizing, oh, yeah, the reason I'm looking at this is because in my problem there's this great big perfectly round sphere. That is how this naturally arose. Right? So this is a reasonable thing to want to be on the lookout for. Okay. All right. Now let's talk about how to parameterize. This is the sort of the opposite process of what we have been talking about. What we've been doing so far is I give you a function, and we've been trying to figure out from that function what is the image. Now we're going to turn it around. Suppose I give you an image. Suppose I give you a curve or a surface. How do you figure out what the function is? How do you find the parameterization? So we call this the process of parametrizing a curve or a surface. There are different ways to parameterize things, different circumstances, different tricks can work. And by the way, once we get into chapter 6, I believe it is, we are going to do a ton of parameterizing of things, and we will talk more about parameterizing techniques at that time. But while we're here, I want to show you a great one. This is very often the way to parameterize a curve or a surface. This is what I call a graph parameterization. It is the name is motivated by the fact that this is how you parameterize graphs. And in some sense or another, most curves or surfaces are graphs. So, in some, maybe in a different coordinate system, maybe in polar coordinates, maybe in spherical coordinates, but one way or another, most, not all, but most surfaces and curves are graphs. So here's the idea. This is just a tricky observation. It's just clever, right? But I'm going to show you the cleverness, and you may capitalize on this cleverness. This is a tool for your toolbox. Here's the idea. Suppose you have a curve which is a graph. Reminder, that's what it means in rectangular coordinates, for a curve to be a graph in two dimensions. So y is a function of x. Clever observation. If we were to let x equal to t. Now, by the way, notice if x is equal to t, then that means that t, since t takes on all values, that means x is going to take on all values, right? If we were to let x equal to t, well, that kind of tells me if x is equal to t, then we want to be on our graph curve. That means that y has to be f of t. And notice what we have then is position on the curve, deliberately set up to be on the curve because I chose y to be f of x. Right? I have position on the curve as a function of time. I have now a parameterization of that curve. It works so nicely. This is just lovely tool for parameterizing. So algebraically, here's how we write it down. If you were looking at a graph of f, then that is a parameterization of that graph of f. Everybody see how that trick works? Questions? Yep. Yep, sure. So, we make a seemingly arbitrary and unjustified choice to start with. I'm just going to choose x to be t. Now, whenever you make an unjustified choice, you have to confess the possibility, well, I may be making a choice that ends up being unreasonable. I may have just painted myself into a corner here. And I confess, yes, I cannot justify this, and I'm personally liable for all of the negative consequences that follow. Right? But I'm going to make that choice anyway, because, hey, I can crumple up a piece of paper and throw it away. It's fine. Right? Let's see what happens if I let x equal to t. And by the way, I want to remain on this curve. Y is equal to f of x. Well, if x is t, then this says y equals f of t. Which means my y coordinate needs to be that, f of t. And here I have then a parameterization. X and y are given by t and f of t, and that traces out that curve because x takes on all possible values. That allows me to get to every point on this curve. And for any given value of x, I will have the correct value of y that puts me on that curve. So this traces the whole curve. It's just sometimes you get lucky. Are you happy with that? Okay. Is everybody else? Oh, sorry. You can do it whenever you have a graph. Right? Now, y'all heard me give the big speech that, hey, graphs, don't hang your hat on graphs, right? Not everything is a graph. Circles are not graphs in rectangular coordinates. So this does not work for circles. But there's a variation of this where we're going to fix that. It turns out that in a very large number of cases, things you want to parameterize are graphs. So whenever it's a graph, yes. Now, related point. When you're going to use this trick, two things. Not only does the curve have to be a graph, but notice I need to know what is this function whose graph it is. You've got to be able to correctly identify the function. And so FYI, it's just, in B, for, warning to the user, you've got to be able to correctly identify what is the function of x, which when I set it equal to y, defines that curve. And we'll, talk a little bit more about that in a few minutes. Okay, so I'm a big fan. By the way, this works for surfaces as well. And I'm not going to draw the picture. Did I draw? Oh, I did. Look at this. So suppose you have a surface. And suppose that surface is a graph. Now, reminder, when you have a graph, if you have two input variables and one output variable, then the graph means for every point down here in the xy plane, you get a corresponding height. Effectively, this f tells you how to lift the plane up in different amounts in different places to make this surface. Right? So with a surface in 3 space, the function whose graph you're looking at is a function of 2 variables. Well, let's take the same strategy. Let's, without any justification, just choose to risky move, but let's just choose. Fingers crossed. Let's hope I get lucky again for x and y to be u and v. Oh, well. hey, if x and y are u and v, then that means that unavoidably z has to be f of uv. And again, we have position in space, x, y, z, given as functions of two input variables, u and v, and we have parameterized this surface. How are we doing? Everybody see? You see how this is kind of the same trick, right? The same, let's get lucky, hopefully it'll work out to where this will be the world's easiest parameterization because the first two coordinates are super simple formulas, and we just make it work. So this is a great trick. I'm a big fan, yeah.
Nomenclature-wise, you're just replacing x and y with m and v to not be confusing, right?
For a u and v, that's a u.
And v,
Yeah. Well, yeah, there are different points of view you can take on this. Some people would like to have x, y, and z as functions of x and y. I mean, you could argue that, what's the difference? X is e, y is v, right? Just cosmetically, it rubs my fur backwards to have the same variable playing the role of being an input variable and an output variable. It just gives me the willies, right? So I prefer to, let's always in a parameterization use distinct variable names for input variables versus output variables. And if the formula is trivial, okay, I'm good with that, right? That's, yeah. But, yeah. Then you make a reasonable inquiry, yeah. And some people will do as you describe. I prefer not to. I prefer that we not do that. Yeah, right. Yeah. Everybody okay? All right. So now here's a variation of this. Yeah. So when we say this was a graph, okay, yes, this is a graph, and that's what a graph looks like. Let me refine that statement. This is okay. It's a graph, but how about if I were to call this a rectangular graph? It's a rectangular graph in the sense that one of the rectangular coordinates is a function of the other two rectangular coordinates. So along those lines, we might ask, what about a polar graph or a spherical graph? Something like that, right? And I'm going to point out that what we really need in order to make my trick work is to be able to write one of the coordinates of a coordinate system as a function of the other coordinates in that coordinate system. If you can do that, if you can write one of the coordinates in terms of the others, then this trick is going to work with a little bit of a variation. For example, suppose I know r is a function of theta, right? And so a circle has r as a function of theta because r equals 1, or constant, right? So it's not a rectangular graph, but nevertheless, a circle does allow me to view one of the polar variables as a function of the other polar variable. And the observation then is, again, you can just plug this in as needed. Now, the one extra step is you do have to recognize that because we want to parameterize, I do want to find rectangular coordinates, x and y. So I'm going to have to sort of, don't forget to make that step. I do need x and y. Those are therefore r cosine theta and r sine theta. But it still remains that if you can solve for one of the variables in terms of the other, you can just plug that right on in to there and notice that you get position as a function of a single input variable now. Theta, which if you like you can think of as time. But still, it's position as a function of a single variable. So, for example, if r as a function of theta, that's a wacky curve in the plane. R equals e to the power of sine theta. Yeah, hard to say exactly what that thing looks like. But I can totally parameterize that thing. I can't draw it very easily, but I can parameterize it because r, being a function of theta, plug that in, and all this really says here is position is r cosine theta, r sine theta. It's just this trick applied to that curve. So, neat fact, you can parameterize stuff that you can't even draw, which is nice. It's a very powerful trick. Okay, here is a spherical version of that. Don't forget we have a spherical coordinate system. Right? There it is. There's the conversion from spherical to rectangular. And I make the same observation. If you can solve for, let's say, rho as a function of phi and theta, then toss that on in there. And the result is position xyz as a function of now only remaining two variables, phi and theta. That's a parametric surface. So I call this a spherical graph parameterization. And likewise, I call this a polar graph parameterization. And this is just a graph parameterization. You can say rectangular graph parameterization if you want. Okay. Let's see here. Last example. Now, this last one, there's yet another additional step. Here, notice none of the variables has been solved for in terms of the others. Right, I've just got some random equation. I really don't want to have to draw a picture of this. This is not rotationally symmetric. This does not look like an easy transformation of something I already know, what it looks like. I guess I could do cross sections. Whoa. Right? That looks nasty. So I am not going to try to draw a picture of this. But I can parameterize it. No big deal. The parameterization is going to require solving for one of the variables. And notice that even though there's a lot going on, it is not that hard to solve for y. Now, it'd be really hard to solve for x. There'd be some transcendental stuff going on here. I mean, x is both inside of an exponential and outside of an exponential. I don't know how to solve for x. Likewise, z, inside of an exponential and outside of an exponential. So I can't solve for x. I don't know how to do that. I can't solve for z. Ooh, I couldn't possibly. But y, no big deal. Solve for y. Once you have solved for one of the variables in terms of the others, then there you go. Our trick is to let the easy variables be the parameters. So let x and z be u and v, and then y. Let's see here, the x and z that I just decided on. Put those into there. Y then has to be that. We just parameterized this horrifying surface that I cannot draw. Okay. All right, I'm a big fan. There are some other kinds of parameterizations that we'll talk about later on, but not now. Okay, this next section is a ton of examples. And as I always do, I'm mostly going to skip these examples. Y'all aren't going to skip them, but I'm going to skip them. So this is one of the many examples that we're going to find in this course where, again, I don't do all of the examples. There's not enough time. It's nearly 500-page book. We can't do all of them, right? So there's going to be a treasure trove of additional examples in this section, and I hope you'll look at them. I am going to say a few things, and that is I just want to point out, I hope everybody remembers the vertical line test. So this curve here is a graph. By virtue of the fact, or let's say we can see that this is a graph because it passes this vertical line test. Do they still call it this in high school or whatever? Okay. So point being, because it passes the vertical line test, it is reasonable that we can say that then for any given value of x, there is exactly one corresponding value of y and therefore I can call that y, whatever is the y value corresponding to this x value, I can call that is the value of the function whose graph we're looking at here. Okay. So as opposed to, on the other hand, this curve is not a graph, right? Fails the vertical line test. So said differently then, if I were to make the assertion that this is a graph, then I would be responsible for saying, yeah, well, what's the value of the function for this value of x? Well, for this value of x, if this were a graph, then that function would have to take these three different values. Functions can't do that. Functions have to be well-defined. You give me an input value, that's got to be a well-defined output value. So this is not a graph. Okay, here is the surface version of that. And it's totally analogous. This surface here passes the vertical line test. This surface here fails the vertical line test, and by intersecting this vertical line intersecting twice. So that's not a graph. Everybody see, it's the same idea, just applied with two input variables, and likewise the other ways. Okay. Cool. Okay, so there's two examples in here that I want to do. Okay, so we're going to start with this one. Basically, all of these examples are about how do I, here's a curve, or here's a surface. How can I represent that thing algebraically? So, and I want to point out that, well, if in certain conditions are satisfied, maybe it's a graph of something. And how do you find that function that it's a graph of? Maybe it's a level set of something, in which case it would be a level set of a different function. How do you find that different function? Maybe it's an image of something, namely maybe we can parameterize it. These are all going to be different functions though. Right? So in the same way, remember we were talking about how, for a given function, the graph of that function is not the same as a level set of the function. Right? We drew some pictures. Level sets and graphs are not the same thing. So for any given function, level sets, graphs, and parameterizations are completely different, and images are completely different pictures. Well, likewise, for any given picture, if it's a graph of something, that's different than what it's a level set of, which is different from what parameterizes it. So, totally expected result. But anyway, let's play this game for a line in R2 that goes through these 2 points. And I'm describing this line without algebra because I don't want the algebra to give away what the answer is to some of these questions. So anyway, that line, not hard to persuade yourself. The equation of that line is this. And now let's go through and ask, is this a graph of something? Is this a level set of something? And is this something that you can parameterize? So step 1, is this a graph of something? So let's think, is this a graph of something? Is it a graph of something? What is this a graph of? Let me tell you the landmine, what a lot of students get wrong here. A lot of students are not sufficiently careful with the terminology and mistakenly will talk about the graph of an equation. A lot of students will say, hey, yeah, this line is the graph of y equals 2x minus 1. And that's an equation, that's not a function. Right? Keep in mind, when you say graph, that word graph describes a process by which you're going to take the function you were given, you're going to create a new variable. Set that new variable equal to the output values, and then write the resulting equation. If you've already got an equation, I don't know, that doesn't fit. This is a square peg round hole situation, right? So this is the graph of that function, 2x minus 1. Right? Everybody see the distinction? So this is a function, this function f is a function from R1 to R1, right? It's got one input value, gives one output value. This function f of x equals 2x minus 1 is a function whose graph is that line. Again, if you write, you just got to be careful about how you use the terminology and how you express your answers. You have to make sure to always distinguish yourself in what you write from a student who does not understand these points. Right? So if you write, this is the graph of y equals 2x minus 1, this makes it impossible for me as a grader to distinguish you from a student who doesn't understand the difference between a function and the graph of a function. Right? So you've got to be ultra careful about. You might say that in these questions, this is largely a question about strict proper use of terminology. It's not really like it's an algebra problem. I mean, think about how much algebra went into answering this. Middle school level algebra, right? That's not the purpose of this question. The purpose of this question is to use the words right and to interpret everything appropriately. Okay. So that's the function whose graph is this line. Now, next question. Is this y equals 2x minus 1, so this line right here, is that a level set of a function? Now, a lot of students would say no, because level set means something equals constant, and neither side of the equation is constant here. But keep in mind that equation is morally equivalent to y minus 2x plus 1 equals 0. Now, my writing is not, let me try that again. Y, there we go. And here, notice, we have, in fact, a level set. Because I've set something equal to a constant, I have a level set of that function. Notice this is a function of two variables. It's a function of x and y. And this function of x and y, a level set of it is obtained by setting it equal to a constant. So in this case, if I take the 0 level set of this function, then I get this equation, which is morally equivalent to that equation, in that it just as well describes that exact same line. So both of these are the equation of that line just as well. How are we doing? Is everybody on board? Everybody see the difference? Okay. So so that second function that we're interested in is that. Just as I suggested, notice that the function whose graph is the line is not the same as the function whose level set, or a function, one of whose level sets is the line. These are very different functions. Okay, now, before we go on to the parameterization, let me just remind you why we care about this. Very often, we're going to want to understand geometric objects. Fantastic tool for understanding geometric objects is calculus. Calculus is something you do to functions, right? So one of the ways we're going to understand this curve up here is to use calculus tools that we know. Okay, well, we're going to develop some calculus tools of graphs. And, well, if I want to understand this curve, using the calculus of graphs, I better apply the calculus of graphs to the right function. I better apply it to the function whose graph is my curve, right? If I apply the calculus of graphs to this function, it doesn't make any sense at all. I will get wildly wrong answers. Dramatically, catastrophically wrong answers, right? And likewise, we're going to learn some calculus of level sets. I'd better apply the calculus of level sets to this function whose level set actually is that thing. If I apply the calculus of level sets to this function, it doesn't make any sense, right? Again, dramatically, catastrophically wrong answers. Okay, so it is very, very important to see and be careful about these distinctions between these kinds of constructions. So last example, can I parameterize this thing? And you can parameterize it different ways. different techniques. One thing you could do, for example, is notice, here's a point on the line, and here is a direction vector for the line with a subtraction. Or, if you prefer, you could use the graph parameterization, right? So this would suggest a parameterization. Take your pick. Again, there are many parameterizations for a given curve. There is no single right answer. But one parameterization comes from the chapter 1 approach that I described. Here's a base point and here's a direction vector. That's a parameterization. Note all three functions different, as they of course should be, because they relate to the curve by way of different processes. And we're going to see a calculus of graphs, we're going to see a calculus of level sets, and we're going to see a calculus of parameterizations. They're all different, appropriate to their constructions. Okay, let me pause for a moment. Anyone have any questions? This is a really important example, in my opinion. By the way, if you want to see more examples of this kind of thing, there's another one right here for a plane in 3 space, and you can take a look at that. I won't go through it here, but it's nice practice. Also, there are a bunch of my old midterms on which I have made questions kind of like this, because I continue to think that it's important, and I don't do it every year, right? But I do use it a lot. So lots of more examples of this kind of thing on those old exams. By the way, you're welcome to look at my midterm exams from past summers using this book. But you're also welcome to look at all my old midterms from old semesters using the other book. It's the why don't I not say it? But using that other book that Duke uses for semester courses. And this kind of question shows up a lot on my old midterms from those offerings of Math 212 as well. Okay, okie dokie. Moving along. A bunch of more examples I'm going to ask you all to read. So last one before we move on to the next section. No, let's take a break. It's 11:05. Sorry to be... I lost track of time there. So we'll take a break and we'll come back and do this example and then move along.